Okay, then let's start first. Yeah, our first program. So first speaker is Chen from University of Minnesota, and he will tell us about anomaly and invertible field theory of higher form symmetry extended group cohomology. She please start.
Okay. Yeah, thank you. Yeah, thank you for your introduction. I am Shi Chen. I come from the University of Minnesota, and I was learning here in YTP for quite a few months. And I really like this place. Okay, the topic of this workshop is about generalized symmetry. And I suppose many speakers will talk about the many interesting topics. So here I will give an appetizer for everything. So I will just talk about some very elementary and simple observation in some basic structure of generalized symmetry and anomaly. And in this talk, I will focus on invertible symmetry. I know many speakers will talk about non-invertible symmetry, but I will just focus on invertible symmetry. Okay, and I will try to look at the anomaly of higher form symmetry and to show some interesting structure. Yeah. So first, let me start from the very elementary part. What is anomaly and how do we understand it? Okay, so when we say there is an anomaly in an n+1 or n-1 dimensional system, then we always think about some n-dimensional bulk. And the anomaly is captured by some n-dimensional invertible field theory through anomaly inflow. That is to say, so we know that anomaly means something is not gauge invariant if we do a gauge transformation to the background gauge field. And such a gauge non-invariance can be compensated by a bulk invertible field theory. So this is anomaly inflow mechanism. And from this point of view, we can characterize and classify anomaly by the higher dimensional invertible field theory. Okay, so which means studying anomaly is equivalent to studying invertible field theory in some sense. Okay. Then given anomaly inflow, so we can try to describe anomaly by the partition function of the invertible field theory. So here I give some example. So here is this C, W, and A, those are background gauge fields. This gives us some classical Lagrange, which means the partition function of this invertible field theory. And typically, we will see many, for example, cohomology operations like punctuation square or Box-10, or if the symmetry is continuous, we will see some Chen-Simons form. Then our task, or say one important task to study anomaly and the invertible field theory is to classify all such partition functions. And nowadays, after many efforts in the literature, people already found some good description for the classification. Yeah, so the classification is given by a certain generalized cohomology, which is, sorry. Which is built out of the classifying space of the symmetry. Okay, so I will continue to be elementary. So I will tell you what is classifying space. So the classifying space, according to its name, it classifies the gauge field of symmetry, of course, invertible symmetry. In the case of zero form symmetry, I think we are very familiar with the form. It's given by something we usually denote by BG. If we consider higher form symmetry, we should add a superscript here. We should increase the number here. So it's B plus 1G. Mathematically, this corresponds to some operation called delooping, which means that if we consider the loop space of the space Bx, and then we will recover the space X itself. Of course, this equivalence is in a weak sense. It's not a isomorphism, but instead it's an equivalence as A infinity spaces. Yeah, but anyway, so if G is discrete, then this B and G is precisely the Ellenberg Maclaurin space, KGN, yes. Okay, and this is the case for a single P-form symmetry. However, typically we can have many different symmetries of different forms. And in general, they can form some non-trivial structure. In particular, the higher form symmetry can extend the lower form symmetry. So we can get something like a higher group. In the presence of a higher group structure, the classifying space will also become more complicated. So if there's no non-trivial higher group structure, then the classifying space is just some direct product of all the individual classifying spaces. But however, if we turn on a non-trivial higher group structure, then we should turn the direct product into a twisted product. Or more rigorously, we should use the fibration. Yes. Okay. So I will often move this time. Okay. So yeah. So for in the two group case, we should consider this kind of fibration, and the classifying space X will sit in between. So it's a sort of twisted product. So if we have three group, then the structure is much more complicated. We have two layers of such fibration. Okay, so in general, for N group, we will have a tower of such fibrations. It's usually called a Postnikov tower. Okay, so when the group are discrete, then this X is a topological space with vanishing higher homotopy groups. And for the lower homotopy groups, each pi I exactly equals to GI. So this gives something called the homotopy N type. Therefore, so we can see that given a homotopy N type, we get a classifying space for some discrete higher group symmetry. Yeah. So this is some basic knowledge about classifying space. And then, so we said that in order to classify the anomaly, we have to consider some generalized cohomology built out of this classifying space. So there are many constructions depending on different perspective and different properties of your physical system. However, in several years ago, people have found quite good universal answer for such construction. So this is given by oh, so what happened? Anyway, so do we have something like a stick? Thank you. Yeah, so it's given by this kind of construction. It's shifted Anderson dual of some Thorne spectrum. Thorne spectrum means some spectrum related to the Bortism. So here I give some example. So for example, if we consider some simple bosonic system, we should take this Thorne spectrum, and then the cohomology will be determined by this short exact sequence. For example, if we consider the target, the classifying space to be trivial, then we can see that the 3D Kitaev's E8 phase, which I mean, roughly speaking, the E8 Chen-Simons theory will be classified by exactly this object. Okay, so if we consider simple fermionic system, we should change the MSO into this M spin because we want a spin structure. And then we will get another similar exact sequence. So also, for example, if we consider Z2 zero form symmetry, then the 3D GU11 Z8 phase can also be classified by this scheme. So if we consider more complicated physical system, we will encounter more complicated spectrum and more complicated cohomology. However, so we believe that such a Thorne spectrum and Anderson dual will give us a universal answer. Yeah. So now I have quickly summarized what we know about the anomaly. And I present some systematic picture for our current understanding of anomaly. So if you have any question at this moment, you can raise your hand or catch this microphone. Yeah. Okay, so if no question, I will just proceed. Okay. Okay, so far, every story sounds quite systematic, but also quite, how do you say, profound or is it difficult? Because we use many interesting but complicated mathematical structure here. However, perhaps when you learn anomaly in your first class, you encounter some simpler situation where you can find a simpler description of anomaly. So now I'm going to remind you those simpler descriptions. So it's an alternative description instead of this systematic approach. So let's go back to the most elementary level. Let us consider one-dimensional system, which means we just consider quantum mechanics. Okay, we consider the anomaly of some finite symmetry in a quantum mechanical system. And we know that it should be given by a projective representation. And what does it mean? It means that, okay, so this yellow line is our space-time. Here, now, of course, just a time. And then we put two operators corresponding to group element G1 and G2 on this line, and we try to fuse them into a single operator. Then we will encounter some phase. So this is just as an anomaly, or say projective representation. And this phase has to satisfy some conditions. That is, it has to satisfy the associativity, which means that if we have three operators, 1, 2, 3, we have two ways, or say two orders to fuse operators to reach a single operator 1, 2, 3. So if we require this diagram to be commutative, then we should impose this condition on the phase factor of the anomaly. So this is a condition or a constraint on the phase factor. On the other hand, there are also something like a gauge redundancy. So we can freely rescale our operator by a phase. So this rescaling will, of course, change this C2 phase factor here in this way. So therefore, so the anomaly will be classified by actually the thing that satisfies this condition modular this kind of image of this yellow part. So here I introduce two operators. I call it a D. So this D2 just means we obtain this kind of thing on the left-hand side. D1 just corresponds to this part. So this is which one? This one? Yeah, this C2, G1, G2. This is G2, G3. Yeah, this is G1, G2. I'm sorry because it's handwritten. Okay, so yes, exactly. Yeah. So yeah, so I suppose perhaps there are some students, so I can do it more concretely. So for example, let's trace this. We can first fuse 1 and 2. So this gives us a factor of C2, G1, G2. So it's here. And so if we continue to do this, we get a fusion between G1, G2 and G3. So we get this. Yeah. So and then I move them to the left-hand side, so we get a minus sign. Yeah. Okay, so this is perhaps the simplest scenario for anomaly. And what we get is such an interesting algebraic object, which is usually called the group cohomology of group G, of course, at degree 2. Now I will continue this introduction, and let me just raise. I'm sorry. Because as I just said, so we should understand anomaly by anomaly inflow. So it's the same situation here. We can also try to understand this projective representation by anomaly inflow. So, and the bulk is nothing but a two-dimensional classical digraph return theory. This is important. It's classical. It's not quantum. Okay. So which means gauge fields are background gauge fields. And then we can consider this kind of scenario. So here, this yellow web is part of the digraph return theory in 2 dimensions. And then this blue line is a boundary of this 2-dimensional theory. So it's our 1-dimensional system. So we can say that if we try to push this boundary a little bit into the bulk, then we can kill such a vertex in the bulk. So if we put this face on this vertex, then we can obtain some phase factor when we do this transformation. So this is precisely the anomaly inflow picture for this 1D anomaly. And for later convenience, I will introduce the dual picture because later I will raise up the dimension. Yeah, but if I raise up the dimension, it's very hard to draw these kind of pictures. So I have to introduce the dual picture. So by dual picture, I mean, I just dualize all the lines. So I get the line perpendicular to them. So the vertex is transferred into a triangle. And then we arrange the gauge fields in this way. And we should put a digraph return weight on this triangle. Okay, so then we get a classical digraph return theory, and we get the anomaly on the boundary. Okay, so now let me just raise up the space-time dimension by 1. So let's consider the 2-dimensional anomaly. So this is also some familiar situation to us. It's the anomaly is captured by the F move of some web of topological operators. So if we try to rearrange this kind of web into this, then we will get an additional phase. So this is anomaly. And just like what happened in 1D case, so there are also conditions for this anomaly. So that is, roughly speaking, we can call it two associativity. It's not a serious terminology. Okay, and which means that if we follow some different order to rearrange this web, and we will get the same answer. So this will give us some equation called the pentagon equation, and it has 5 terms, just like this. So we see that it's very similar to the equation on the previous slide, but it just gets slightly more elements. Now it has 3 elements instead of 2. And in addition to this constraint, we will also have redundancy. So now the redundancy is not the renormalization of a single topological operator. Instead, it is the renormalization or the rescaling of the junction of operators. And recall that in the 1D case, this phase factor is precisely the anomaly in that case. But here, in 2D, this factor is not the anomaly. It's actually the redundancy. Yeah, it's generally true. So the something in lower dimension will become a redundancy in higher dimension. Okay, so then if we try to consider the transformation of C3 under this redundancy, we will get this equation. So again, the anomaly will be classified by this kind of algebraic structure. So it's a third group cohomology of the group G. So we can also play the similar game to think about the anomaly inflow. So as I said that because the dimension is very high, so I cannot draw it. So I have to introduce the dual picture. So in the dual picture, the F move can be described by this kind of rearrangement. Yeah. So, and then from this picture, you can easily recognize what should be the bulk. What should we do with the bulk? So the bulk is still a digraph written theory, of course, classical. And then because the dimension is 3, so we should consider a tetrahedron instead of a triangle. And then we should put a digraph weight on this tetrahedron. So we can say that the back two faces of this tetrahedron is precisely this figure. The front two faces of this tetrahedron is precisely this figure. So the F move just means, we just how to say, push forward the boundary from the backward surfaces to the outward surfaces. So yeah, so this is what happened in 2D. And okay, so yeah, in general, we can play the same game in higher dimension. So we will obtain the well-known structure called group cohomology. Okay, so now here comes a question. Can we try to understand other aspects of generalized invertible symmetry by this kind of algebraic construction? Here, I mean, in particular, can we try to tell such a story in terms of algebraic quotients, operators, for higher form symmetry and higher group symmetry? And the second, can we use this kind of language to describe generalized cohomology, that Anderson duo of the sum spectrum, that formidable object? And last, can it cover continuous symmetry? But this is not so relevant. So I will focus on these two questions. So already we know something. So for example, we can try to generalize the group cohomology by introduce some fermionic line or a fermionic higher dimensional operator. Then we can try to upgrade this group cohomology into group super cohomology. So in such a way, we can capture a lot of fermionic anomalies. So this is done many years ago. But we ask for more. Can we go beyond that? And also, how do we treat high form symmetry and high group symmetry? Okay, so this is a question I propose now. Yeah, but I have to apologize because I will not answer this question in this talk. So in this talk, I will just push a small step further. Yeah, I will just talk about some very simple generalization of the group cohomology, which is, I think, interesting enough to share with everybody. So that's why I decide to talk about this. So what I'm going to talk about is I will consider higher form symmetries, but I will assume that the higher group structure is trivial. Okay, and then I will just consider ordinary cohomology. I will not consider generalized cohomology. So as you see, this is so simple compared to what I wrote on the last slide. Yeah. So, but still, we can already see some interesting algebraic structure here. Okay, so before I go into this part, do we have any questions? Okay, then I will just continue. So, I'm sorry, this should be 2. Oh, yeah, I don't know why I wrote a 3 there. Okay, so let's try to consider the invertible field theory. Or now we know that it is a digraph written theory in the presence of higher form symmetry. So let's consider P-form symmetries. I mean, we may have a bunch of symmetries from 0 form, 1 form to n form. And I will denote each P-form symmetry gauge group by G P plus 1. So which means G1 means 0 from symmetry, G2 means 1 from symmetry, and so on. And then I will just do what Digraph and Wheaton did. We try to triangularize the space-time and discretize the gauge fields. Okay, so if the space-time dimension is n, then in a triangulation, the most elementary cell is an n simplex. N simplex is spanned by n plus 1 vertices. So I will use 0, 1, n to denote those vertices. And then all the other higher dimensional objects inside this simplex can be expressed by some combination of the vertices. For example, if I wrote 2, 4, it means a link that connects vertex 2 and vertex 4. If I write 1, 2, 3, it means a triangle spanned by the vertex 1 and 2 and 3. Okay, and I will always use the increasing order. I will always use increasing order. This is very important. And this also means I will pick up a particular orientation. For example, if I write 2, 4, I of course suppose the orientation is from 2 to 4 instead of from 4 to 2. Yeah, the same for higher dimensional objects. Yeah. So, and then I will, in order to describe the set of higher dimensional objects, I will introduce this notation. So this n, comma k. So I will define that this nk notation means the subsets of all the vertices that contains k plus 1 elements. For example, n1 just means the set of links. N2 just means the set of triangles or say faces. Okay, and then a gauge field on this n simplex will be specified by such a map. I call it a capital A. So here, this nk means the set of links, triangles, and so on. And this gk, as I said, it's a group for the higher form symmetry. So for example, if I write A01, then it lives on the link. So on the link, I will put a G1 element. And G1 element means a 0 form symmetry. So similarly, if I write A012, then I put an element on the triangle. So on the triangle, I will put a 1 form symmetry. So it belongs to G2. Yeah. So so on and so on. So this is how I arrange the gauge field on this simplex. And then this is not enough because the gauge fields are highly constrained because we have to put the locally flatness condition. So actually here comes the assumption about, as I said, I assume there's no non-trivial higher group structure. So if there is a non-trivial higher group structure, then the gauge fields are not locally flat. But here, I will just suppose we have no non-trivial higher group structure. And then when we impose a locally flatness condition, so those gauge fields A are no longer independent of each other. So in order to express the independent degrees of freedom, I need to try to introduce some ansatz. Okay, so in order to introduce these ansatz, I will introduce a new notation. It's still called nk, but however, now this is no longer the set of subsets of the vertices. It's because I remove 0. So we should not regard this as a set of vertices. We just take it abstractly, some abstract thing. And then this X will also contains K elements instead of K plus 1. So this is just an index set. So it has no direct geometric meaning. Okay, and then I will take these ansatz. to express the gauge field on an n-simplex. So, I claim that according to these ansatz, I can get all the locally flat gauge fields on this n-simplex. So let's try to see some example. Yeah. Oh, by the way, what's the time now? Okay. So let's see some example. Yeah. So remember this figure. Yeah, I draw it in some previous slide. So it corresponds to three-dimensional digraph written theory. And on that slide, we only consider zero form symmetry. So we only put group elements on links. So then actually, the way we arrange those group elements on that figure precisely fits into these ansatz. It's a special case of these ansatz. So we can check that. According to these ansatz, we can write down these rules. And we can check that, oh, it's precisely the same as this figure. So in such a way, so this ansatz is a direct generalization of the old ansatz we use for group cohomology for zero form symmetry. So we can check some expressions. For example, we still consider this tetrahedron. Then we can consider some surface such as 0, 1, 2, the bottom triangle. And then according to this ansatz, it should equals to G12. And if we do it with A013, this triangle is no longer one element, it becomes two. Yeah. So it's G12 times G13, and so on and so on. So of course, if we consider higher dimensional case, we can get more complicated expressions. But everything just comes from this ansatz. And this ansatz is a direct generalization of the old ansatz for group cohomology. Yeah. So do you have any question about this ansatz itself? So
could you remind me what was the large A?
Large A, okay. So yeah, I should say something to my computer. I'm sorry. Yeah. So the large A is the gauge fields on a simplex. Yeah. So yeah, let me use this figure. So for example, A01 just means something I put on this link, and it's a zero form symmetry element.
So in that way, you said that the gauge field becomes flat, locally flat.
Yes, by this ansatz.
Oh yeah.
Becomes locally flat.
Thank you.
Yeah. So actually, after this slide, I will not use A anymore because I already introduced these new degrees of freedom. So I will focus on G because they are independent of each other. Yeah.
Here, do you already assume G is an abelian group, or is it?
Okay. Oh, that's a good question. Yes, because we know that for higher form symmetry, the gauge group must be abelian due to the dimensional reason. We can easily exchange some higher codimensional operator. Yeah, exchange their order. Yeah. So for this higher form symmetry, we have to assume the gauge group is abelian. And you can also understand it from this ansatz, because this ansatz contains several products. If the order of product is very important, then this ansatz has some ambiguity, right? So in order to kill that ambiguity, so we have to assume that the higher form symmetry must be abelian. But for zero form symmetry, it's okay, because for zero symmetry, we just have a single product. And then we just do it with a little order, like 1, 2, 3. So for example, this A12, you cannot write it as, for example, G2, G1, G3. That's not allowed. So for zero form symmetry, the order is fixed by just the natural increasing order of the numbers. Yeah. But for higher form symmetry, it doesn't matter. Yeah, it's abelian. Yeah. Okay. So now we know that by this answer, we can express the locally flat gauge fields on the bulk triangulation. So then let me address a pure mathematical question related to this. So let's consider the following scenario, which will be useful later. So let's try to embed an n-1 simplex into an n simplex. Because an m simplex has many m-1 simplex as its faces. Okay, so let's do the J's embedding. Here, I mean, okay, so if the index of the vertexes is less than J, and then I just map those two vertexes. If the index of the vertex is greater or equal to J, then I will shift it to the larger index, which means that in this embedding, I will just how to say, stay away from the vertex J. So I will get the higher dimensional surface opposite to the vertex J. So this is the J's embedding I define. And then let's consider, so under such an embedding map, so what's the pullback of the gauge fields? So if we write everything in terms of the capital A, then the pullback is straightforward. Yeah, that's just what you see. Yeah. But however, now if we express everything in terms of the variable G, then this form of the pullback will become quite complicated. It's like this, because we'll have to rearrange the independent degrees of freedom. So that's why the expression becomes more complicated. Okay, so because this expression is quite complicated, so I also give some examples. So let's consider the embedding from a 3 simplex to a 4 simplex. So, and this dot means the J of the J's embedding. So for example, if for this dot equals 0, I mean the embedding just meets the vertex 0. And it maps to the vertex 1, 2, 3. Yeah. So, okay, so let's look at this table. So we can see many familiar entries. So for these link variables, so here we just have one single index. So they are link variables. They are zero-form symmetry. So from this table, you can recognize something familiar, right? This is precisely what appears in previous slides about the group cohomology of the zero-form symmetry. Yeah, but here we can also consider higher dimensional surfaces. So now we get another similar but more complicated table, or say pullback map. So and also for two-form symmetry defined on a tetrahedron. Yeah. So at this point, I think one can understand why I need to consider this embedding, because it will definitely appear in our final expressions for the differential operator. Okay, so now we just finished one job. That is how to arrange gauge fields, or say locally flat gauge fields on a triangulation. So next, we will try to consider the digraph written theory on this background. So then the digraph written theory, of course classical, is specified by a weight on each n simplex of this triangulation. So formally, it's given by this map. So the target space is U1 because of this EI something. The domain is the set, or say the collection of all the group elements I put there. So for example, if the dimension is 1, if you consider 1D digraph written weight, then we just have a link. So it's just a C1 and the variable is just G1. So if we consider 2-dimensional case, we get more. We get, because 2-dimension, which means we have a triangle. And then we get 2 edge variables and 1 surface variables, and so on. So and one should be careful. So the number of those G's are the independent degrees of freedom for locally flat gauge fields. So they do not equal to the number of the links of the triangles and so on. Yeah. And they are much less than that. And then we can try to hook up such a differential operator. The differential operator is nothing but the boundary sum. I will explain why this is the correct differential operator, but here, let me introduce its structure. So by boundary sum, I mean, so suppose we have a n-dimensional digraph weight theory. So we have a set of weights. And then we can consider a n+1 simplex. And then we just put our n-dimensional digraph weight theory on the surface of this n+1 dimensional simplex, or say on its boundary. Yeah. So then we sum over all those weights with some sign. This sign corresponds to the orientation because we want to follow the Stokes law. And then this partial, this phase map I introduced just now, give us the embedding. Yeah. So and yeah, please remember that this J has some complicated expression, but is totally under control. Okay. So then let's try to read off what this operator looks like. So let's consider D1 C1. So this map D1 will map C1 into some C2. So now it has this kind of variables. And then this gives us expression. So we see that the only meaningful part is the zero form symmetry. So this is precisely what I wrote for the quantum mechanical anomaly, some projective representations. You can see this expression there. Okay, so for D2C2, we get more complicated things. So if we set all the higher form symmetry to be trivial, if we just look at the zero form part, okay, so we can see that, oh, this, I mean the yellow part. And so sorry, blue part, yeah. And then this is also some familiar expression I wrote in the 2D anomaly. But however, now we have something more. We can see that we have something for the one form symmetry. So it's a yellow, the red part. Oh, I don't know why I like yellow so much today. Okay, so if we set all the zero form symmetry to 0, then we can only get the blocks for the one form symmetry. So that part corresponds to the anomaly, or say digraph weight theory for the one form symmetry only. So if we continue to consider higher dimensions, we can get more complicated expressions. So still, we can see that the zero form part, the yellow, the blue part, is still the same as the ordinary group homology. But now we have something on top of it. We have the contribution, the red part, for the one form symmetry, and the yellow part for the two form symmetry. So yeah, those expressions are generally complicated, but you can just write on them quite easily according to the form of the phase map. Okay, so then why this D is a correct differential operator for what we want? That's because it's physical meaning. So let's consider the cohomology associated with this differential operator, the boundary sum operator we just discussed. And then we can see what does it mean by the numerator. The numerator tells us our theory is invariant under the rearrangement of the triangulation. That must be the case, right? Because triangulation is just some auxiliary tool, and our theory cannot depend on it. So this kernel tells us our theory, yeah, is indeed independent of the triangulation. Okay, and the denominator gives us some gauge invariance or the gauge redundancy. Because if some n-dimensional digraph rate is the boundary sum of some n-1 dimensional digraph weights, then they will always sum to a trivial element in n+1 dimensional compact manifold. So yeah. So it's a little bit tricky, but I think it's not hard to understand. Yeah, it's roughly speaking something like a d squared equals 0, that sort of thing. Yeah. Okay, so then we can try to cook up this kind of object, which is just some generalization, some simple generalization of the group cohomology. Okay, and it reduces to ordinary group cohomology when higher form symmetries are trivial, as I just showed on the previous slides. And I have to emphasize that the ansatz I made is not needed to obtain the resulting cohomology, because people can do it very abstractly. People can just forget about the ansatz, and people just work with the gauge field capital A with the constraint, with the locally flatless constraint, and just abstractly write down this cohomology. So of course, the resulting cohomology will still be the same thing. So yeah, that's not a surprise. But however, here I would to emphasize that in order to obtain such a good-looking differential operator, for of course, the good-looking depends on people, yeah, and that naturally generalized ordinary group cohomology differential operator. So this ansatz is needed. So for this purpose, the ansatz is needed, and I think this ansatz is quite useful because by this ansatz, we can literally express everything in terms of some explicit algebraic equations. So I think that from that point of view, this ansatz is quite nice. And it's better than nice. Yeah, but before that, let me, okay. Sorry, I forgot I made this slide. So, okay, so on this slide, I'm going to give some example of the anomaly in higher dimensions, because in the introduction part, I talk about anomalies in 1 dimension and 2 dimension. So here, I will give some example about anomaly in 3 dimension. So according to the ansatz, yeah, because the ansatz will help us to arrange those group elements. So if we can see that. So in 3 dimension, everything becomes more complicated. So we have vertices, lines, surfaces, and the surfaces corresponds to 0 form symmetry because it has codimension 1 now. So and this part is given by this kind of arrangement. So this is the most general rearrangement for the anomaly in 3 dimension for the 0 form symmetry. So and for the 1 form symmetry, so the rearrangement is like the following. So it's like the change from this shape to this shape, and the group elements are arranged according to the ansatz. Okay. So and I think most of us are more familiar with the description in terms of the anneals. When we talk about the 1 form symmetry anomaly in 3 dimension, we will typically talk about the breeding between abelian anneals and so on. So that's the more familiar language. But here, I would like to point out that this language might be also very interesting and also tells us many interesting phenomena. So for example, let me tell you how these 2 languages are related. So we can just set all the group elements to trivial. Let's just make this G12 non-trivial. Then we can try to trace the lines that contains G12. So on the top figure, we have this V. Okay, so on the bottom figure, we have another. So we have this G12 and like this V and this. So this is a line for G12. So now let's turn on another non-trivial element. Let's say G24. So G24 corresponds to this arc. in the top figure. So on the top figure, the arc of G12 and G23, they do not intersect. However, in the bottom figure, they intersect. So we see that the G24 corresponds to this line. So we can see that these two lines intersect at the point, and then we get a phase according to anomaly. So this precisely corresponds to the onion picture. Yeah, but this picture is more, how do you say, complicated. It contains more things because when we talk about anion fusions, we always keep in mind the junctions. So the junction have 3 legs, but here we can see that in this figure, a dot usually has 4 legs. Okay, so but anyway, these two descriptions are related. Okay, so then let's go back to the general story. So then this construction of the extended group cohomology is good in the sense that it equals to the topological way. It equals to this cohomology of the classifying space. And because I said that we consider trivial higher group structure, so the classifying space is just a direct product of individual classifying space of each form symmetry. So then we can quite easily, or say quite conveniently, show they are equivalent or they are isomorphic by using our ansatz for the left-hand side and using the so-called Dodecke correspondence for the right-hand side. So the Dodecke correspondence, which I will not go into the detail in this talk, gives a particular convenient construction for this space, for the Ellenberg-McLean spaces. And then if we try to evaluate the cohomology of those spaces according to the Dodecke correspondence construction, then we can see or say recover our ansatz. But of course, there are many, many intermediate steps, but I will not go into the detail in this talk. So anyway, this means our construction is anyway correct, as it should be. So this is not something surprising. Okay, so this is my talk today. So I tell you some very simple observation in the anomaly of higher form symmetry. So, and as I said at the end of the introduction, so my general purpose is try to do this thing, try to find a good algebra construction for general invertible symmetry anomaly. So which should include higher group symmetry and generalized cohomology and so on. So, and in this talk, I just do a very, very, very tiny step to show some interesting structures. So I hope this can entertains most of you. Yeah, so thank you for your attention. Yeah.
Yeah, thanks very much for interesting talk. So if you have any questions.
Sorry? For Zian, so you mean the answer for what? For this cohomology? You mean for this cohomology? Yeah, it's precisely the same as the cohomology on the classifying space. For Zian? Okay, so it's just the familiar result, I mean. So if we consider BZN, yeah, you consider this kind of thing. So
no, I meant when Zn is the one form symmetry.
Oh, you mean one form symmetry?
Yes.
I see.
I just wonder if you get the familiar result that it's Z2n.
Yes,
there is an important factor of 2.
Yeah, exactly. You get that. It depends on the even or not oddness. So you get Zn. Okay, this should be 3 or 4. So if n is odd,
yeah,
you get this, and if n is even, you get this. So you can see that it does not capture the spin structure part. So if you want to get a pure Zn here, you must go beyond to consider something like a supercohomology. Yeah. Thank you, Zohar. Yeah.
Other questions or comments?
Just to like reproduce this generalized cohomology classification to some extent, you could just use the GU and super cohomology or the Brownfield-Morgan model. There are some models that depends on that written in terms of the cochains, and you can just apply those models to describe some particular generalized cohomology, and just to describe the part of the spin Bordism group, say. That part seems very easy.
So it's a commentary.
Yeah, that's
Okay, yeah, you're right. Yeah, I think it's quite hard, for example, to describe the E8 Chen simons. I have no
yeah,
idea,
so that's for like
Yeah.
that class, yes. I agree.
Yeah. So I agree with you. Yeah. So, but there are some algebraic parts that can be captured this way. I suppose. Yeah.
And can I ask another one if there is no other one?
Sure.
So another thing that happens in the literature is that when there is one form symmetry, the anomalies of zero form symmetries are not well defined. How do you see that in this formalism?
Oh, you mean symmetric factorization?
Yeah.
Actually, yeah. So how do you say? In this part, it's kind of independent. I mean, for example, if you have a theory with some particular symmetric factorization, then its anomaly is fixed, right? So you get some anomaly. So, and this is okay because I regard symmetric factorization as a particular way to match some anomaly. So here, I just talk about the anomaly itself.
Okay.
So
To extend this observation for higher group, non-trivial higher group structure, at which step do we have to change your strategy?
Okay, so the key point is the locally flatness condition. So this is already pointed out by the very first paper by Lyon and perhaps Kapstein. I'm sorry, I forgot the details. So it's the locally flatness condition. So roughly speaking, so if you consider this tetrahedron, so okay, tetrahedron. So as I said that here I impose local flatness condition, which means that if you go around this triangle, if we sum over all the link variables, we get a trivial thing. But however, in general, this is not the case. So if you have a higher group structure, then this will give us some non-trivial thing. You will get some additional thing according to the I'm sorry, it's a reverse. So if we sum over the one form part, so we sum over all the group element on the surfaces, on the triangles, then we should not get a non-trivial, should not get a trivial element. And that element, what we get should depends on the zero form part. Yeah, so that's how do you say, that's what we should take into account.
So the difficulty comes from putting nice answers, taking into account those.
Yes.
Conflicts.
So in principle, you can do everything in a very abstract sense. Then you can still try to prove that what you get is precisely the same structure on the classified space. You can still do that. But to me, I think that's not so useful because I want to get more concrete or say explicit expression for the cogents. So then for that purpose, yeah, we need some good answers. Yeah.
Okay, so it's about time. So if you do not have any other questions, so let's, or does anyone have one? Yeah. So let's then close the first speech.
Thank you.